Okay, so I'm going to talk about the MERLiN project, which was in answer to the call about essentially looking at metrics for overshoot. And MERLiN reflects my thinking that quite a lot of the negative emissions space is a little bit magical thinking. That is, it's not a technology that has yet been demonstrated to work at scale. So I'll start with that. So there's two things I want to talk about. I've got 5 minutes, so I'm going to be quite short. The first thing was essentially looking at how you might build carbon accounting for negative emission technologies. And that was led by Matthew Brander. And what we did, or what he did really, was a literature review to find papers, screening and snowballing, so find papers that cite other papers that were cited, and found 55 papers. And the summary of that is, or the key summaries from that are: one, consider permanence, that is, carbon in the Earth system, or the fast Earth system, that is where it might interact with the atmosphere, has an extremely long lifetime, hundreds of thousands, tens to hundreds of thousands of years. So I think it's important to consider permanent. So for example, forests are not permanent stores of carbon. We talked about burning forests earlier. And also in a climate change world or a societal change world, those forests may disappear or not, at least maybe, okay? Use the reality principle. That is, count carbon emissions when they occur and count removal when it occurs. So budgets should be reported on that basis. Use consequential life cycle analysis. Nets will need to be deployed on a planetary scale. And one thing I was struck by the talks earlier was in some ways the relatively small scale, or under 10 gigatons of carbon dioxide per year, and at the moment we're emitting about 40. So they'll have planetary scale effects through changes in pricing, so people need to consider that. So that was one of the bits of the study. The other bit of the study we were looking at was to use a fast, rather older system model called FAMOUS to essentially look at what happens if you overshoot and then recapture CO2. So this is an experimental design. Is essentially we have simulation of historical carbon emissions. Then which it turns out this model is, well, it's not very oversensitive. It's on the high end of sensitivities, not greatly. And we concluded that so if we don't have sulfur emissions and therefore aerosols, we think we included methane and everything else. So we'd already breached the 2-degree warming point by 2020 in that simulation. So one thing I'd also like to make a little point for, there is, as the IPCC reported, quite a large uncertainty in the translation of CO2 and other emissions and other forcings to climate change. And Rand Sutton has a really nice paper on it. We should think more about tail risks as a consequence of that. So let's be careful. I often hear median 50-50, so just remember that. Okay, so we then have a positive CO2 pulse, and they're very large. They range from 250 to 1,000 gigatons of, petagrams of carbon. Zero emissions after that point, and then the negative pulse sometime later. So what we're essentially saying is we're going to be overshoot in this period. We want in time and amount, and essentially we're trying to see if there's a simple metric. And to first order, there are two ways in which climate change impacts us. So first of all, surface temperatures essentially change the surface climate. So things like changes in extreme rainfall, extreme temperature, hurricanes, whatever, are driven by surface temperature. First order, patterns matter, but we're just going to look at global surface temperature. The other impact is via sea level rise. So I'm going to talk about those a little bit separately. Okay, so basically this is the findings because it's 5 minutes. So these are the red cut. This is the atmospheric CO2 from the various pulses. The reddish colors are on the warm. The darker the red, the more CO2 is emitted, ranging from 1,000 petagrams, 500 petagrams, 250 petagrams. These are huge. Really, the system behaves quite linearly at these amounts, so that means if we're down in this little range, we can also assume linearity. They all decline. That's what you'd expect. The ocean's taking up the carbon. Intriguingly, when you remove it, down here, you get a negative pulse. There's too much carbon in the ocean. You remove it faster than the ocean can outgas it, and so actually you end up with negative reduction in concentrations, and that essentially that's showing it in ppms, that's showing the atmospheric concentration in petagrams. This is time from 2000 to 2500. But essentially by 2500, so 500 years after the start of this, we're back to where we were. So there's a delayed response. Here's temperature. So that's our first order. And there's some sensitivity to whether you do this. I can never explain. The blue stuff is when we did this relative to a pre-industrial state, essentially. So there's some background sensitivity. And I think you might like to say that's within the realms of modeling uncertainty. But the first order, you essentially respond very rapidly. The temperature responds pretty much instantaneously to this change in this pulse of CO2 within a few years, much less than a decade. So the carbon we emit basically causes climate change now. It's not next generation's problem, it's our problem. Okay, so, and then when you draw it down, you do, particularly on the cold end, in the cold base references, you actually get quite cold because, again, you've reduced atmospheric CO2 concentrations below current values because it can't get out of the ocean fast enough. So that's the air temperature. Here's the average ocean temperature, which is a proxy for stearic sea level rise. Doesn't include ice sheet melt. And essentially, we see this kind of very slow pattern. This is average temperatures of sort of 0.6 degrees. Pretty much a little bit of sensitivity on the background state, but not very. And then declines. It declines somewhat faster in the warm scenarios than the cold. But this is essentially linear. This is looking at the impact on volume average ocean temperature as a function of emission times time in overshoot. So for surface temperature, response depends on total amount of carbon. That's nothing novel. For oceans, response depends on how much you emit and how long you're in overshoot for. Okay, so let's finish with key findings. So model surface temperature responds very rapidly to carbon pulses within a few years. So that means carbon emitted, the carbon of the society we are emitting today is causing us damage today. And and response is proportional within about 10% of the size of the carbon pulse. Doesn't really change over that period. It's fairly constant until you remove it. Volume average ocean temperature, stearic sea level, responds slowly. It's a fairly linear rise during overshoot. So the longer the overshoot is, the more sea level rise you get. Post-drawdown, quite a lot of sensitivity to background state, which essentially allows some different forcings for similar atmospheric carbon changes. Temperature post-drawdown is close to reference, so you return, so it's irreversible. Sea level isn't. Okay, so there's some policy-relevant conclusions. Emissions have impact now. If we have overshoot, we will live with more damage. And we'll pay a sea level price, and we can't trade them off. So we will not return to the climate that we would have had in the absence of overshoot because we make a trade-off between surface temperature or sea level rise. The longer in overshoot, the larger the sea level response. It's linear up to a couple of centuries. And there's some very odd things with negative atmospheric CO2 when drawdown. So one doesn't want to be in overshoot for long. Overshoot costs through damage plus long-term impacts.